All right, here's example number 1b from 16.4. So we just did number 1a and we saw that divergent integral where the area keeps growing and growing and growing. Let's do another example and see what happens. So I have this graph 1 over x squared, and I want to find the area underneath this graph from negative infinity to negative 2. Woo, what happened there? There we go. From negative infinity to negative 2. So if I have this graph and I want to go from negative 2 and then I want to go left, 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 left all the way, I wonder if our area will be a convergent integral where we can actually find a value for the area, or if it's just going to keep growing and growing and growing and be a divergent area. Well, let's see. Let's take this improper integral and let's rewrite it into the definition of an improper integral. Let's go from a number to negative 2. We're going to call it a to negative 2. And then eventually let's make that a approach negative infinity and use our limit process. So the first thing we always need to do anytime we see an improper integral is rewrite it using those definitions. So we need to go from an a to a b, and eventually if that a needs to go to a negative infinity, we can apply that limit process in the end. Did you also notice that I brought that x to the negative 2 up to the numerator to make it a positive 2? So that way I can use my power rule for integration and find the antiderivative. So let's use that idea. Let's add 1 to my exponent and divide by that new exponent. So I ended up getting x to the negative 1 over negative 1. And we're still evaluating it from a to negative 2. I'm then going to bring that x to the negative 1 down to the denominator so that I can make my exponents positive. So your problem should now look like mine. I have the negative 1 over x. We're evaluating it from a to negative 2. And eventually we want that a to get really, really, really small and go to negative infinity. Now we can apply the fundamental theorem of calculus, plug in our upper limit, plug in our lower limit, and we end up getting this kind of expression. We have a negative 1 over negative 2. Two negatives make a positive 1/2 there, right? And then we've got minus a negative 1 over a. I'm going to simplify that a little bit, calling it a 1/2 plus 1 over a. And eventually, don't we want that a to approach negative infinity? We want it to be really big but negative. Now think about that. If we plugged in a negative infinity here for a, my top would be a 1, but my bottom would be a really big negative number. Now remember, as my bottom gets really, 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 really big, what actually happens with my fraction value? Yeah, doesn't it turn to 0? And so now that a has gone to negative infinity and it's gone to be a really big negative number, my expression turns into a 1/2 plus 0. And so what's 1/2 plus 0 is 1/2. So that means the area underneath this curve, starting at negative 2 and going to the left as far as you can possibly go, really just ends up adding up to a total of 1/2. This we call a convergent integral. It's kind of interesting to think about when you graph this function and you look at it versus graphing this 1 over x function from example number 1a and you look at it and you kind of compare the two different areas and see how one of them converges to only a 1/2 where the other one diverges and keeps growing and growing and growing. Sometimes you get an actual area value, convergent. Sometimes the area just keeps growing and growing and growing enough that you can't add it all together and get an actual real number for its value.